The first transfer path we're going to look at is our conduction transfer path. And so in this case, our transfer path is provided by wires, cables, circuit board traces, etc. So we have some physical connection through some type of conductor between our source and our victim. So oftentimes our culprit is going to be our power supply lines, and so we'll look at why that is here in a little bit. So oftentimes our culprit is our power supply line. We can also have issues in our ground leads. So ground leads can also be an issue. But typically these power supply lines are going to be our sort of first place that we want to check if we're having what we suspect is conduction EMI. And so the reason that our power supply line is typically an issue is because these are the conductors that are connected to all of our active components. So connected to all active components. And so in order to visualize that better, let's take a look at a cascaded amplifier circuit, which has 3 stages. So we have some low-level input stage A1, some intermediate stage A2, and then a high gain stage A3 at our output. And so of course I'm sort of simplifying these amplifiers with 1 input, 1 output. If we're talking about, for instance, op amps, of course they're going to have 2 inputs and maybe some more complicated configuration, but sort of ignoring that for the moment, just saying we have some input, some output for each amplifier, and then it's also grounded and then powered. So all of them are connected to this power supply. And so note that our power supply, I've included this resistor R sub P. And so the reason I've done that is we can say that this represents better a non-ideal power supply, which is going to have some internal resistance R sub P. And so it turns out if we have some time varying signal, some radio frequency signal, for example, that is being output from our gain, as this output is changing significantly over its linear area, so as we have something that looks like this, we're also going to get a time varying current that's being sort of pulled from our power source on this power line. So I'm going to use a lowercase I to indicate that this is an AC signal. And so this time varying current I3, as it's flowing through, there's of course this current, we're also going to have DC components going to our other amplifiers, but as this AC component is going through our RP, we're going to have some AC voltage component, V3, which is going to be equal to I3 times RP, which is introduced to this power supply line. And so these changes in I3, as I mentioned, are proportional to our changes in our output over here. So as we see large variations in the output, we can see large variations in that I3, our AC current being drawn on that power line. And again, it's only because we have this non-ideal power supply. If we didn't have that resistor RP, it wouldn't be an issue. So what this can mean then is that if we have this AC voltage V3 on the power line, I3, remember, is proportional to the output. So our V3 is also proportional to the output, and that's coming back in here and it's affecting our input. And so we have this feedback, which in the right conditions can lead to instability and oscillation of our circuit. And so that would just be this time varying signal with no input. And so typically that's not something that we want. So one way that we can fix this is with power supply bypassing. And so in order to do that, between these 2 stages here, we can essentially put low pass filters. So we can put some resistor and some capacitor. And so the value of these resistors and capacitors is going to depend on our application, what frequencies are we using, and what currents are we expecting, what voltages do we have, that type of thing. But the basic idea is now we have these 2 low pass filters. And so ideally we actually want to have our C values as large as possible, because remember our impedance for our capacitor is 1 over j omega c. So if we have a large C, that's going to be a small impedance. So any AC signal we have, so if we have some AC voltage on this power line, it's going to be shorted to ground through this small impedance here. So AC signals are going to come here, and if for some reason it gets past that one, we can short it through ground through this capacitor C1 as well. Whereas, of course, our DC source, our VP, any signal arising from this, is going to see C1 and C2 as being open circuit, and so it's just going to travel along here like normally and power our amplifiers. So that sort of bypassing, that power supply bypassing is one solution that we can employ. And we'll come back and we'll talk about that in a little more detail later on. So power supply bypassing. So one other thing to talk about, sort of looking at a more general circuit, is let's say we want to do some type of diagnostic test. We have some connection, maybe we have some other elements in between here, but we have a power supply, and that power supply is connected to multiple elements. We notice that one of our elements is malfunctioning, so this would be our suspected EMI victim, and we also have another one that we suspect to be the source of our EMI for one reason or another. So what we can do is we can take this connection and we can sort of rewire things in order to diagnose whether or not that's true. So let's come down here and let's start by just pasting that there, and we can say, let's change our connection to do a diagnostic test. So connection for diagnostics. And so what we're going to want to do is we're going to want to break this connection between our EMI source and our EMI victim. And we can leave this connected. We're not really too concerned about that. And so what we're going to do is we're going to connect some separate test supply to our EMI victim. So let's get rid of this. And let's assume we just had that one. So let me move this over a little bit. And let's go ahead and copy that. And let's just say that here we have our separate power supply. So some separate test supply. And so we're going to connect that to our EMI victim. And so if our EMI source and EMI victim, if we've made correct assumptions and they're behaving as we have assumed up here, what we're going to see is that our EMI source, and again, we're assuming that this is for our conduction transfer path, our EMI source is going to be sending some signal along this connection, along our power line, and is going to be interfering with our victim and causing it to malfunction. Well, of course, here, by disconnecting that physical connection with our wire, we've blocked this EMI transfer path. And so if we rewire this and we see that our supposed victim is now operating properly, then we know that our issue is in our power supply line. So as I said, power supplies are usually the culprits. So our power supply line is a good place to start, but we have a couple other things that we need to be aware of and can check as sort of a second place to look as well. So power supply lines are a good first place to look. And so we can, of course, do some simple diagnostic tests like shown above, but a couple other possible conductors to keep in mind and investigate if our power supply line does not turn out to be the case would be any type of metallic chassis or any type of sort of box or metallic casing for our system. And a second one would be any non-electrical conductive equipment. So it might not even be part of our circuit, or not intended to be part of our circuit at least. And so an example of this would be maybe we have some pipe, so something that's just carrying water, for instance, could become conductive if it's just a standard copper pipe. So these are other areas to consider as you're looking to diagnose conductive EMI problems.